If you gather just 23 people in a room, there is about a 50% chance that two of them share the same birthday. It sounds like a trick. Most of us would bet on needing hundreds for something that unlikely. This is the classic birthday paradox, a probability illusion that exposes the gap between our instincts and reality. Why does our intuition get this so wrong, and what hidden mathematics is at work? A classroom fills with quiet chatter as the host steps forward, holding a deck of 365 birthday cards. 23 volunteers line up, each drawing a card and reading their date aloud. The room is tense. Most faces show polite skepticism. The host asks, "What do you think? Is there any chance two of you will match?" A student shrugs. "Not likely. Maybe if we had 50 or 60 people." One by one, the birthdays are called out. The first dozen are all different. A ripple of laughter rolls through the group. But then, as the 17th card is read, a voice calls out, "Wait, that's my birthday too." For a split second, the room goes silent, then bursts into an audible gasp. The host grins, holding up both matching cards. There it is. Out of just 23 people, we've landed a pair. The number isn't a fluke. Mathematicians have checked and double-checked. With 23 people, the chance of at least one shared birthday is 50.7%. It's not a trick or a magic show. It's a simple fact of how combinations work. The surprise isn't just in the math. It's in how deeply it clashes with what everyone expects. The moment lingers, the disbelief hanging in the air, demanding an explanation. Why does such a small group create such a big chance for coincidence? Our minds are wired for stories, not statistics. When faced with a puzzle like the birthday paradox, most people lean on gut feelings, mental shortcuts that work fine for everyday choices but stumble badly with probability. Psychologists Amos Tversky and Daniel Kahneman gave names to these habits. The representativeness heuristic, for example, pushes us to judge likelihood by how much something looks like a typical case. In the birthday scenario, that means picturing one person at a time and thinking, what are the odds this next person matches someone before? It feels like each new birthday is just one more roll of the dice, so our brains expect the odds to climb slowly and steadily, almost like adding one block at a time to a pile. But probability does not play by those rules. Instead, every new person in the room does more than make one new comparison. They form a link with every single person already there. The number of possible pairs grows much faster than our intuition can keep up with. This is called the linear comparison error. We imagine the risk grows in a straight line, but it actually explodes with each new connection. Our memories do not help either. The availability heuristic means we remember dramatic coincidences, but forget the boring non-events, making rare matches feel even more surprising. It is not that people are bad at math, it is that our mental models were never built for hidden patterns like this. The birthday paradox does not just fool us, it reveals the blind spots in how we see chance itself. Suppose you want to figure out the chance that, in a room of people, nobody shares a birthday. Instead of counting all the ways a match could happen, start by asking, how can everyone be different? The answer comes in steps, one person at a time. The first person can have any birthday at all, nothing is ruled out. The second person has 364 options left, since only one day is taken. The third person has 363 choices remaining. Each newcomer has one less day to pick from as the calendar fills up. To find the probability that all birthdays are unique, multiply these shrinking chances together. For 3 people, say, it is 365 out of 365, then 364 out of 365, then 363 out of 365. With every new person, the number on top drops by 1, but the bottom stays at 365. By the time you reach 23 people, the product stacks up like a tower of fractions. 365 out of 365 times 364 out of 365 times 363 out of 365, all the way down to 343 out of 365. This is called the complement path, counting the ways to avoid a match, not the ways to get one. Only after multiplying all these steps do you get the chance that no two people match. To find the chance that at least one pair does share a birthday, just take what is left over. Subtract the no match probability from 1. That is the secret behind the 50.7% figure for 23 people. It is not magic, just a chain reaction of shrinking options multiplied together. This approach turns the problem on its head and gives us a formula anyone can quote. Stack the odds against a match, then flip them to see how likely a coincidence really is. Counting birthdays one by one hides the real explosion happening beneath the surface. Each new person does not just add one more chance for a match, they connect with every single person already in the room. Mathematicians capture this with a simple formula. The number of possible pairs in a group of n people is n times n minus 1, all divided by 2. For 23 people, multiply 23 by 22, then divide by 2. That gives 253 possible pairs. In a circle of 23 friends, there are not just 23 chances for a match, but 253 lines crisscrossing between them. This is where intuition buckles. Most people picture the odds stacking up in a neat row, like blocks on a shelf. But combinations multiply, they do not just add. With each new arrival, the web of connections grows thicker at a startling rate. That is why the chance of a shared birthday rockets up so quickly, even when the group still feels small. Of course, the classic calculation makes some big assumptions. It treats every birthday as equally likely, no seasonal spikes, no leap years, no cultural clustering. In reality, some days are more crowded than others, and adding February 29th or accounting for birth booms can nudge the threshold lower. For example, in places where certain dates are especially popular, a match might pop up with even fewer people. The rule for 23 people is a kind of mathematical ideal. Real life can be messier, but the core idea holds. The number of potential pairs grows much faster than our instincts can track. With the math laid out, the next step is to see it in action. Simulations and experiments put these numbers to the test, showing just how often the paradox plays out in real classrooms and computer models. 1 million simulated classrooms, each with a fresh group of strangers and a shuffled calendar, tell the same story as the math. For 5 people, the chance of a shared birthday barely registers, just under 3%. With 10, it jumps to about 12%. At 23, the curve spikes past 50%, matching the classic prediction within 0.1%. By 30, the odds soar to over 70%. These are not just numbers on a chalkboard, they are the result of running the experiment again and again, letting randomness play out on a grand scale. In university studies, students who watched the probability curve take shape in real time, with bars rising and matches appearing, walked away with a much deeper grasp of the concept. Surveys from the University of Illinois found that after a live simulation, comprehension of collision probability jumped by 28%. For many, seeing the data unfold is the moment when the paradox stops feeling like a trick and starts making sense. The math holds up, not just in theory, but in action. Cloud engineers once trusted 64-bit codes to keep billions of files separate, believing a collision was almost impossible. But as the system grew, the math caught up with them. Out of 100 million records processed each day, it only took a few months before 2 files landed on the same code, a digital birthday match. The result was that data vanished, and 0.02% of users lost access to their files. The post-mortem blamed a classic oversight, ignoring the birthday paradox. In cryptography, the lesson hit even harder. In 2004, researchers proved that the MD5 hash, once a security standard, could be cracked far sooner than expected. Instead of needing 2 to the 128 tries, the birthday rule meant a collision could appear after just 2 to the 64 attempts. An astronomical number, but suddenly within reach of modern computers. A cryptography engineer put it simply, you do not need to fill the whole room, you just need enough people for the ODDS to tip. The same logic has tripped up lotteries too. In 2012, a state lottery ran a promotion with 10 million tickets and 7-digit serial numbers. Officials thought duplicates were rare, In reality, over 40,000 pairs shared a number, forcing an extra $12 million in payouts. The birthday paradox is not just a classroom stunt. It is a warning. Whenever the number of possibilities gets big, the risk of a match grows with the square root, not the total. Ignore that, and the cost can be real. Probability still fools us, even in the age of data. As algorithms shape everything from security to social feeds, the birthday paradox reminds us that our instincts lag far behind the math. In a world built on chance, understanding the hidden patterns is not just clever, it's essential. What surprises you most?